You don't have to record it.
I do,
Okay.
because of all the people that aren't here because of the.
I'm happy to do another
Bennett.
virtually
Okay,
from.
yeah.
Okay,
Oh, Bennett.
I have to do something to get this back in.
Hey.
Okay, so here's my outline. First, I'm going to tell you what a superconductor is. And I'm going to specify a conventional superconductor because we have dozens and dozens of kinds of superconductors around. After I do that, I'll tell you about the place where I'm the chief scientist, the National Magnet Lab. Then I'm going to go into some practical applications and some theory and why we need better superconductors. Along the way, I'll discuss what not a conventional, but an unconventional superconductor is. And I just like to call them strange superconductors. And at the end, I'll go into that analogy I was talking about. And I want to leave you with the feeling that there's been amazing progress recently and a lot of promise for these materials, both for understanding fundamental science and for applications. These are the defining properties of a superconductor. To date, all practical superconductors must be cooled. I will tell you about 3 weeks ago, a paper came out in Nature that said they had achieved room temperature superconductivity. I'm not going into that. It's not practical at all, but it was pretty exciting. Anyhow, all practical superconductors must be cooled to a low temperature, and it's superconducting only below its critical temperature called TC, C for critical. And below that critical temperature, TC, there is zero electrical resistance. We're not talking small, we're talking zero, that you can transmit electricity without any loss. So here I am in Durham, North Carolina. If I had a light bulb here and I had a battery in Portland, Oregon, and they were connected by superconducting wires, it would work just fine. There is no loss. The other thing that they have is perfect diamagnetism, which means it just spits out magnetic fields. And that's what I'm showing below that there, is that that sphere is supposed to be a superconductor, and below a certain temperature, unlike any, even a perfect conductor, it spits the magnetic fields out. That was the sign, this perfect diamagnetism was the sign. So I'll tell you in a second that superconductivity was discovered in 1911. In 1927, this perfect diamagnetism was discovered. I don't know if there's any graduate students out there, but that perfect diamagnetism is called the Meissner effect. And it was discovered by the student Aschenfeld. And instead of calling it the Aschenfeld-Meissner effect, it's the Meissner effect. So if you, the idea there is get your PhD and get out, and so you can get credit. Anyhow, that was a sign that there was long-range quantum mechanical order. And I'm going to define that in the next couple of slides. You can have a 2-slide quantum mechanics, and then things will get a lot easier. But first, I want to tell you what some TCs are, critical temperatures, and how cold is cold. So here's the show. What we talk about in science is the Kelvin scale, and that's the scale here. What we're used to in this country is the Fahrenheit scale. And the Fahrenheit scale, as we know, boiling water is 212 degrees Fahrenheit, ice is 32. And if you go down to absolute zero, so if you go out in the middle of space where there is nothing around you, far from everything, you're 3 degrees above absolute zero, okay? In the US, anywhere in the world, we can get colder than that, where everything slows down as much as possible. Now, why do we use the Kelvin scale? Let's say it's cold outside and it's 0 degrees Fahrenheit. And then the weather report says it's going to be twice colder tomorrow. Okay, well, that doesn't make any sense. You can't multiply the Fahrenheit scale. So we go to the Kelvin scale, where 0 on the Kelvin scale is actually 0 degrees. And so if you have 20 degrees Kelvin and you want to get twice warmer, you go to 40 degrees. So we can use it in our calculations. Now, when conventional superconductors typically go up to about 40 degrees Kelvin, that's still really cold. That's minus 388 Fahrenheit. The high temperature superconductors that were discovered in 1986 go up to about 165 Kelvin, the highest one, or about minus 163 Fahrenheit. So here's a plot that is missing many, many, many points. On the y-axis, it says temperature Kelvin. This is the temperature of the critical temperature of each of the superconductors plotted. On the x-axis, it says year of discovery. Now, I don't know how I did that. Okay, it says it's year of discovery. So what we have plotted here is a few families of superconductors. So when I mentioned that superconductivity was discovered in 1911, that's this one right here. that's mercury. And everything in red is conventional, okay? And we understand why they superconduct. And I'm going to tell you how in a minute. Everything that's not red is an unconventional or strange superconductor. We have approximately 50 families of these superconductors, and they're all incredibly alike in some ways and incredibly different. And the blue up here is the family of the high temperature superconductors that I told you about. Now, almost, by the way, in quantum mechanics, nothing's absolute. Everything's kind of like brushed a little blurry. But almost every one of the unconventional superconductors have this phase diagram. And I'll show it to you several times. I'm just going to define it here, and you'll see it more than once. This y-axis here, okay, is temperature, and the x-axis is a thermodynamic variable. Typically, it's either pressure or changing the composition, like putting in oxygen or putting in another thing, and that changes the amount of carriers in that material. We call that doping. So what this has here is that at ambient pressure or without any doping, we have, in this case, there's an antiferromagnetic insulator, but these are really, really bad metals that are not understood very well. Over on the far right side here, where it's yellow, under high pressure or a lot of doping, it actually looks like a normal metal, like copper or gold. It's called the Fermi Liquid. Now, if we go in between these two things, this is what people have been studying for decades, and I can't get away from it. If we look at the different sides of this phase diagram, why is this going behind? Well, I'll just talk, the arrow seems to go back, there we go, now in front. So if we go down to low temperature and you start releasing the pressure, or removing the doping and measure the properties, we see it's a Fermi liquid until you hit something here. And on this side, when you have all these strange metals, you come over and you hit something here. What happens is you can't make these strange metal and the conventional metal meet at the bottom. What happens, whatever is going on down at the bottom here, whatever is going down in the bottom of that blue dome is hidden. What happens is superconductivity grows out of there. These two phases fight, 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 and we call that a quantum phase transition. And I won't go into that, but we want to understand what's under there, because if you go under that dome, we want to understand why that blue phase forms. And what is that blue phase? That's the superconducting phase. Now I want to stress something here, which is that we know how conventional metals work. That's not a problem. We also know what basically forms a superconductor, and I'll tell you that it's when the electrons are paired in a certain way. And we can actually understand in the yellow area, we can understand the properties. We have equations that we can predict and understand the thermodynamic, optical, and transport properties in the yellow area. In the blue area, under the superconducting dome, we can also understand it. We may not understand exactly why the superconducting pairs form, but they're still superconducting pairs, and we have equations to explain the thermodynamic, optical, and transport properties. That area that's kind of orange with those stars there, that we do not know how to describe. Now, like I said, all these strange superconductors have basically the same phase diagram, but that strange electron or quantum matter that we can't explain is really different for every family of superconductors. So it's a very, very complicated problem. So let's move on a little bit here. Oh, as I mentioned, all superconductors must be really cold. And I said that before. So typically all conventional superconductors need to be cooled below the temperature of liquid air. So if I go back here, liquid air is about 77 degrees Kelvin here, which is about whatever it is, about minus 290 degrees Fahrenheit. And that's really cold. So I work with a material a lot called liquid helium and liquid nitrogen. So these are just examples of liquid air. It's just something to tell you it's much, much warmer than I'm used to working with in my laboratory, but it's still really cold. So yeah, I'll show you, let's go from left to right. If you take, as you know, most materials, when you cool them down, they shrink. I'm doing this, I put these pictures together because I can't do the demos virtually. So, well, it's not in this home. I could do it if I was in my lab virtually. So if you cool down a balloon, it shrinks, okay? If you take a flour and you stick it in the liquid nitrogen and it freezes, this soft, pliable flour, you smash it because it freezes solid and smashes. Now, how cold is cold? I can actually stick my hand in liquid nitrogen and be okay. Not for a long time. We used to do, we're not supposed to. Actually, Grant just gave me this look. When we were in graduate school, physicists are very macho. We used to take deep dewars of liquid air and throw stoppers in them and take turns who could pull out the stopper without hurting yourself. Why can you do that? Okay. By the way, if you do that, you want to keep your fingers separated so you don't catch the liquid nitrogen. So if you've ever made pancakes, you know that if it's not hot enough pan, the pancakes don't come out as well. Now, how do you know the pan is hot enough? You know the pan is hot enough because if you throw a few spits of water on it, the little water droplets run around on the surface and they last for a long time. Why? Because that pan is so hot compared to those water droplets that the water droplets actually evaporate on the bottom and it's running around on a layer of gas. And it lasts longer because that gas insulates the drop from the pan. So we all know if you touch that pan, you're going to get burned. That's because that pan is really, really hot compared to the pancakes. And that's what's going on in the figure above that. You can, if you pour liquid nitrogen on your hand or on the floor, it'll just run around in little droplets because for liquid air or liquid nitrogen, your hand is really hot because these liquids, superconductors, have to be really cold. So that's a lot of interesting technology that we worry about. Now I'm going to give you 2 slides of quantum mechanics, okay? And I'm not going to use equations, but I mentioned that all superconductors we figured out because of this expelling of the magnetic field have long-range quantum mechanical order. As I think all of you know, electrons can be represented both as particles and as waves. All electrons can. Now, if you have a material like this can of whatever this is, this lovely water here, it's not superconducting. That means all the electrons don't have long range order. It's just a simple metal. And the electrons bounce around, and that's kind of a cartoon of what the electrons are doing. And plus in a normal metal, even if you cool it down, because they're electrons, I'll tell you why in the next slide, they can't be in the same quantum state. There's a rule that electrons cannot fall in the same quantum state. I'll mention that again in the next slide. But so that means the phases are all over, there's just random waves. And if you want to explain everything, you're going to need an equation for every single one of those electrons in that material. Okay, there's actually approximations we can use to get around that, but that's the basic idea. On the right side is what we have is if we have a superconducting state, we cool it down and all of a sudden, below that critical temperature, the electrons form into a single quantum state. And the joke is electrons are loners and whatever the state they fall into, they fall together, they're party animals. So how does that happen? Let's go on to the next slide. Okay, so all I want to say also that if I know the phase of a superconductor over here, I know the phase there. You just need one equation to describe that entire solid, no matter how big it is, because it's in a single quantum state. How do you explain that? As I mentioned, superconductivity was discovered in 1911. It wasn't until 1957 that the theory was cracked. So electrons have a property called spin 1/2. Doesn't matter what it is, but we understand that because of that, like a little tiny magnet has this thing called spin 1/2, they can't fall into the same quantum state. But if you have an integer spin, say 0 or 1, you can fall into the quantum state. Electrons are fermions, they can't. Spin 0 or 1 are called bosons, they can. How do you turn electrons into party animals? The second thing is electrons are negatively charged. So how can you pair electrons? And the joke was you can't repeal Coulomb's law. So this is sort of a cartoon of the theory that came up in 1957 by Dean Cooper and Schrieffer. It's brilliant. It's one of, as I mentioned, there are dozens and dozens of correlated electron materials out there, and dozens of correlated electron questions, and only 2 have been solved. This is one of them.
So Dr. Greene, where was this discovery made?
University of Illinois in Urbana-Champaign, about 3 in the old physics building. Yeah. So I was there for 23 years. It's a great place. So the basic idea, and this is a cartoon, and I want to warn you about analogies, right? If you take this too far, it will fail. I had a picture that I forgot to mention before, but if you've ever taken quantum mechanics, there's an analogy that we love that was created by one of the greatest minds of the 20th century, Niels Bohr. And that's the Bohr model of the atom. If you've ever studied it or learned it, it really helps you understand things, but it's completely wrong. So just remember when I use these analogies, don't push them too far. So here's this analogy. It's called the soft mattress analogy. So the electrons don't pair together. It's not like you stick them together with a thumbtack. What happens is an electron, when you go at high temperatures, at high temperatures, like when you're boiling water, the background ions are just going to be moving around a lot. And as you cool it down, things slow down, and then this electron phonon or electron lattice interaction becomes a larger energy than the thermal energy. And when the electron goes through the lattice, it'll be, the lattice is attracted to it because the background ions are positive and the electron traveling through it is negative. And as you can see in the middle bunch of dots, that's what I showed on the very first slide on the upper right, that those ions are pulled in, drawn in to that negatively charged electron. And that's like leaving a wake from a boat in water. So now a second electron sees that positively charged wake and is attracted to it. That's the basis of the BCS theory. So you can think of it, I've improved this soft mattress analogy because they say it's not that these two people are attracted to each other that are in this mattress. It's just that the mattress is soft, so they roll together. I add to make the analogy a little stronger. They really do not like each other. They're repulsed from each other. So what happens is, so one person stays in the center of the mattress where it's all weak and down there, and the other person hangs on to the side of the mattress. Okay, so they repel, so they're holding onto the edge of the mattress. The one in the center leaves. The other person said, I could relax now, and rolls into that depression that was left by the first person. That encompasses many, many things that I won't go into, but it tells you there's a time delay and it tells you there's a magnitude, how deep, how strongly they're paired, and over what time scale and distance scale they can be paired. This is completely understood now in conventional superconductors. We got the equations, we can explain everything. What I will tell you is this kind of pairing occurs in all superconductors that we know of to date. But the mechanism of pairing is not the electron lattice interaction. The electrons are paired by something else. I have a paper in review right now where we're showing that electrons are paired by some kind of magnetic interaction that hadn't been seen before. And so the pairing mechanisms in all classes of unconventional superconductors remains elusive even after decades. And unconventional superconductors were discovered in the 70s. I just want to tell you a little bit about a perfect diamagnetism, and I'll show you a picture later on. But if you take a superconductor and levitate it over a magnet, it will always float and it'll be stable. I'll tell you why in a second. So the superconductor is on the left side and we see it's floating. And why does that happen? And it turns out that no matter if you flip it or not flip it, it's always going to float. So if that magnet on the bottom has north pointing up, whatever happens with that superconductor, north will always be pointing down. Without going into detail, what happens is the electrons on the surface create their own magnetic field to exactly repel the applied magnetic field from the magnet below. Okay, so it's always going to say, I don't want you here, get out of me. I don't want any magnetic field in my bulk. And so it'll just, the electrons will move around to make its own magnet and repel the applied magnetic field. Okay, so here's an example here. In this case, we have the superconductor is the cool thing on the bottom, and on the top is a very strong magnet. And the history of these magnets is also very interesting, but that's another story. Look how stable that is. So that's not true with magnets. Harshaw's theorem dictates that two magnets are not stable. Two DC magnets are not stable. And how do you do that? But that makes it look practical. So there have been, we all know about levitated trains that exist. Most of them don't involve superconductivity, like the one in Shanghai does not involve superconductivity. But in Japan, they have at least two maglev trains that use superconductors. Their first maglev train came out in the 60s using conventional superconductors. And my science friends in Japan say that it only went for a kilometer, but it went for long enough to take their funding agents for a ride. Now, this is actually a prototype of a high temperature superconducting maglev train in Japan. They will have practical applications. But I want to tell you one more thing about superconductors, and that is there's two types of people. No, I'm sorry. There's two types of superconductors, type 1 and type 2. Type 1 superconductors get rid of all of the magnetic field. And if you put in too much magnetic field, you break up, you can beat the pairs and break them. Just like high temperature will break the pairs, too much magnetic field will break the pairs. What was also invented in the 60s was something called the type 2 superconductor. What that means is that it doesn't get rid of all the magnetic fields. If I can point on this, yeah. So what we see here is that within the superconductor, there's magnetic field lines that penetrate, okay? And then around these magnetic field lines are those kind of superconducting loops that expel the superconductor from the rest of it. So the blue area on that picture on the left is superconducting, but inside of those, what we call vortices, where the magnetic field lines go through, are not superconducting. All type 2 superconductors have this happen, and only type 2 superconductors are practical. They're the only ones that can take the high field. One thing that we study in applied superconductivity is you need to pin those magnetic field lines. Why? Because as I mentioned, inside the vortices, the material is not superconducting. So if those vortices can move, then you're moving normal metal, not superconducting metal, and you will dissipate energy. So now we're going to have something fun here.
Ladies and gentlemen, are you ready? Then please welcome from the physics department at Ithaca College, Dr. Matthew C. Sullivan and the quantum levitator. Doctor, thank you so much for joining me. Now this is a quantum levitation track, correct?
It is indeed.
All right. Well, thank you so much for coming on to help me crush Jimmy with quantum levitation. Nation, as I'm sure you know, quantum levitation refers to the phenomenon whereby the magnetic flux lines flowing through a type 2 superconductor are pinned in place despite the electromagnetic forces acting upon them. I learned that from the inside of a Snapple cap. Now, Dr. Sullivan, can you confirm that if my ice cream quantum levitates, it is undeniably the ice cream of the future?
Absolutely. That's just science.
Okay, excellent. All right, here we have some of my Americone Dream. It's available in mini cups, which Jimmy's is not, okay? And I will confirm that it is delicious. And now, are you ready to send my ice cream into the future?
Certainly.
All right. Okay. Ice cream of the future, engage. It's levitating! It's levitating! Here, put it down for a second. There you go. Whoa! Oh, Jimmy, look. Look, Jimmy. It's levitating. Eat it, Fallon. Eat the future. We'll be right back. Hit it. Ladies and gentlemen.
Okay, it really is levitating. So anyhow, so that's the introduction to superconductivity. And I won't be able to get through all my slides, I'm sure, but I'd like to get through some of the things that we do with the National High Magnetic Field Laboratory, which are called the Mag Lab. First of all, if you go just Mag Lab, you'll find this website. It's actually, I think it's nationalmaglab.org or something, but it doesn't matter. Just Google Mag Lab. And we have a lot of really fun things on there. Lot of not just news and events, but things you can learn. We have millions of hits a year of Magnetic Academy, interviews, behind the scenes of the Magnet Lab, what goes on inside of a magnet, and they're really fun, and I really recommend it. We've got a great group doing that. Now, the National High Magnetic Field Laboratory is in 3 locations. The main campus is in Florida State University, and that's where we have the strongest field magnet in the world. If I have this right now, it's about 1,000 times your, I think it's 500 times your refrigerator magnet field. It's a 45 Tesla hybrid magnet. We also have the largest NMR magnets and MRI magnets in the world. We can do MRI at 21 Tesla. I'll give an example later on. So we have 4 user facilities and 2 laboratories in Tallahassee, and that picture in the upper right is the laboratory, and it's really big. If I walk from my office to my lab, then my Apple Watch gets very happy with the steps. Okay, down at University of Florida, we have 2 facilities. One is the high B over T, and there they can only go to 17 Tesla, but they can also go to 1 milli-K. By the way, that's one of the few nanokelvin facilities in the world, but we don't put a field as high as that at nanokelvin. And those experiments can take weeks to months. The other, what we have in University of Florida in Gainesville is the Advanced Magnetic Resonance Imaging and Spectroscopy facility. And that's where we do a lot of in vivo work on animals, et cetera, at very high fields. And I'll give an example of that. Then at Los Alamos, we have the pulse field facility. And if you look at that big picture there, if I can point, I'm always worried about touching this pointer. This is the generator, and that's the size of a normal human. So it's big. So I recommend going out there. This goes into 101 Tesla pulse. No one comes anything close to that non-destructive. And we're at that point, we want to work into the 120 at some point. We're working on that in long range plans. Now, I don't need to go over this again, I've already said all that, but I want to tell you that we are primarily a user facility, and we attract research from all over the world. And this is what we call our Delta Airlines map, where you can see that Gainesville, Tallahassee, and Los Alamos are clearly hubs of Delta Airlines. And if you're interested in going to those hubs, and you know, we've had thousands of users a year across hundreds of institutions and worldwide, and almost 300 institutions throughout the world in 2019. And I want to point out, newcomers are welcome. 25% of the PIs every year are first-time users. And so our Mag Lab staff can help you work things out. You go online with that website that I told you, and you can see, oh, I want to do an experiment on this magnet and why. You fill out an application, and it's gone over, and it's free to use. You have to get there, and you can stay with me. I have a big house. But first-time users are welcome to join. And we publish a lot of papers. So the National Science Foundation that keeps us going is happy with us because we have a lot of bang for the buck. We have 3 major research themes: materials, energy, and life. And I'll just give an example of each. So I mentioned that dome before, okay? And we want to understand, why does high temperature superconductivity emerge out of the dome? And so you can see here that at 45 Tesla, we can only break some of the superconductor. This is that phase diagram where this is temperature, and this is, in this case, it's doping, but in some cases it could be pressure. And we have this dome that I talked to you about. Underneath this blue dome, it's superconducting. But as you apply higher and higher field, you bring that dome down. And by 80 Tesla, you still don't completely kill it at lowest temperature. But we've learned a lot by pushing this thing down and understanding what's going on right at the base when these 2 different phases are fighting with each other. And we're hoping by understanding that, we'll be able to design new and better superconductors. I'm going to give 2 other examples. One is ion cyclotron resonance. There's a 14 team. I didn't update the slide I've been working on our MagLab renewal, but now there's 21 Tesla high homogeneity wide bore magnets. And what they do is basically, it was invented to put in a spit of petroleum and look at the mass. And it's a mass spectrometer on steroids. And so there's hundreds of thousands of molecules in oil, and it's different for every oil well. And so here's an example, the time of flight that was used without what we can do, that's the resolution. So if you want to do mass spectrometry, the best before ion cyclotron resonance, that green curve is what was possible. And this is what we can pick up at the Magnet Lab. Okay, so what is this good for? I have lots of examples. Our 21 Tesla magnet now can measure the difference in complex fluids of the mass of 3 electrons. It's amazing. So for petroleomics, for instance, did BP and Exxon strike the same well in the Gulf? Each time they drill a well in the Gulf, it costs about $1 billion. We can tell them exactly if they hit the same reserve or not. And what if there's an oil spill? We can do the forensics. We can tell you exactly from what oil head that oil came from. You can imagine we did a lot of work for deep horizons. Proteinomics. This is just one of, we do work on global warming, and I was going to update this and I couldn't, but I'll give you this example. The P53 protein is a very studied protein. As many of you may know, that the folding of a protein determines its functionality. So the P53, depending on its folding, can be healthy, what do you call it, or cancer, whatever it is in between. It can be just all kinds of things. We do a hydrogen deuterium exchange and measure it, and we can tell if it's malignant or non-malignant due to that protein folding. And it's used, this stuff is used in all kinds of things and looking at amyloids, et cetera, et cetera. Now I want to go on to the life example 1. I mentioned 21 Tesla. The commercial, if you've ever had an MRI, I think everyone over about 25 has had an MRI, maybe everyone over 10 now. And the best part of an MRI is you get to go inside of a superconducting magnet. But the commercial magnets that are used for MRI are typically 2 to 4 Tesla. So that's about what you use. And what happens in an MRI is they line up the hydrogen in your body with this 2 to 4 Tesla. You're inside of this big magnet. And then they put a lot of RF, just radio frequency signals on you, and they can measure how these things light up, if there's where the water is, and that's how you measure tumors, because you can measure that there's more water in one spot than another spot. But that was low resolution. So the commercial will give you about a millimeter diameter resolution. At the Magnet Lab, we can do micron resolution. However, I have to warn you that you don't really want to put a human in a 21 Tesla magnet. The magnetic field won't hurt you, but the radio frequency irradiation you have to do to take the image is actually can get dangerous. So it's used on non-living things. But let's do something different. Let's unlock the periodic table. My last example is MRI across the periodic table. So what we're doing now is not imaging hydrogen like we image water in our body. We're going to image, in this case, sodium, and we do a lot of different things. Why do you want to do sodium? Well, it turns out that when cells are dying, they uptake sodium. We don't understand the mechanism completely, but we don't have to. So it turns out, I learned at the Magnet Lab, you can buy a mouse with brain cancer. So here's a mouse, I didn't know that. Here's a mouse with a tumor, and we're imaging the tumor, low RF fields and 21 Tesla. So there's no danger to the mouse. The mouse get up and run around after they're done with this. And what do? You look at the tumor and you give it chemotherapy. You wait 4 days and you image, and you can keep that going until that tumor lights up. Here's an example of a tumor lighting up. It's brighter. What does that mean? It means there's more sodium in that area than there was earlier. So that area is uptaking sodium, indicating that those cells are dying. That gives you confidence that that chemotherapy regime may be successful. So this is still in the prototype stage, but it's very exciting. So I'm gonna running out of time. Can I have 5 minutes or okay. So so why do we need better superconductors? So the applications. The only good applications are where other materials won't work. You want large magnets like we use at the magnet lab? We use a lot of superconductors in our magnets. I mentioned MRI and supercolliders. On the lower left, a discovery at the Mag Lab in 2019 changed what was going on at CERN. And now materials discovered at the Magnet Lab are being wound and sent to CERN specifically for the high luminosity upgrade. So that's pretty exciting. If you want to detect very small magnetic fields, which might be useful in quantum computing, I'm sure they will be, you need to use a superconductor. I'm going to give some general examples of energy, grid and turbines, and also for fundamental research. Strange superconductors are playgrounds for broken symmetries, and we don't really understand them, exactly why they superconduct and what some of this electron matter is. So I just want to point out that we do have a 21st century energy challenge, and I threw these in just to bring this up because this was in the news recently. I took this out of my talk because this hasn't been active in a while, but I brought it back in. It turns out in the United States, you've seen this in the news lately, there are 3 separate grids. And Mr. Edison and Mr. Tesla had a disagreement. Mr. Tesla won, and these grids are AC circuits. And they're not connected. There's the Eastern interconnection, there's the Western interconnection, and the Texas interconnection. And that, as you know, can have problems. And also it was argued that they should be connected for Homeland Security. So there was something started by the DOE many years ago that was canceled. It was picked up by private industry, and it seems that nothing was going to happen. But this would be an amazing application. It's called the Tres Amigas Superstation that would be in New Mexico near these grids. And it would be high capacity superconducting connections. What you do is you take the AC from the grid and you convert it down to DC, and then you invert it up to AC again, and you'd be able to connect the grids. You need to do that because they're AC, they're out of phase. If you just connect them, the power loss would be substantial. And I'll skip that one. Well, people probably like this. They're doing more and more for wind power generation. If you make the transformer out of a superconductor, you could make it 5 times half the size and weight. And considering the turbines are getting to be the size of 737s, this is substantial. And one of my students is selling these now in Mexico. And you know, the reason why Tres Amigas and this is good is because you have to cool these things with things like liquid air, and they're localized. It's not over a long distance. And I want to remind you again about this thing that we have our conventional superconductors in red, okay? And this is this dome that's ubiquitous to everything else on here. And most of the families of unconventional superconductors aren't even listed here. Here's a few examples. This was discovered in the early 1970s. These are called heavy fermion superconductors. This is the high temperature cuprates. These are the high temperature things called dichalcogenized. There's organic superconductors. This is another 2 sets of families that have iron in them. And they all have these domes, okay? They have usually antiferromagnetic over here, a simple metal here, and this strange stuff here. And I'd love to go into detail, but I won't. So what is this strange quantum matter? What it's not. It's not what we already do understand. It's not things like copper, silver, and gold. We know how to calculate those properties. It's not a superconductor. Even if it's unconventional, if it's in the superconducting phase, we know how to calculate things. The general definition, okay? If we calculate the properties of a simple metal, it's calculated by knowing the crystal structure and the atoms that make it up. So if you have niobium, or if you have steel or whatever, you just put in what makes up, they're called DFT, there's computational methods that have been created, and we use these all the time. You just put in the crystal structure, where the atoms sit, and what the atoms are, and you can calculate the properties, okay? So the electronic properties in a simple metal can be calculated by the crystal structure and where the atoms are. In these kind of funny, strange metals, it doesn't work. In experiments, the electrons just do strange things. Like even at high temperatures, the electrons will form they'll form into clumps, they'll line up or get 1,000 times the mass of a conventional metal, of a free electron. So conventional metals, as I mentioned, at high temperature, in conventional superconductors, at high temperature, it's just a simple metal, okay? And you have electrons running through this background. And at low temperature, you have Cooper pairs. And in this case, I'm using the example of the phonon background moving in, of the lattice background moving in. These are solved problems. Now let's look at unconventional superconductor with this dome phase diagram. At the far right, you have a normal metal, okay? Below TC, you have Cooper pairs. So probably not paired this way, but they're definitely Cooper pairs. And on the left, you have, above TC, all above here, you have these strange metals. What this is an example of here, it's a cartoon of something that I've studied a lot myself. It's called electronic pneumaticity. So at high temperature, like 100, almost 200 degrees Kelvin, the lattice, if you look down on it, looks square, but all of a sudden the electron says, I don't care what you're doing, I'm forming little stars, okay? Or sausages, depending on your favorite, whatever you're doing. But it forms these things that are like 8 lattice constants long. And we don't really understand that. Or the electrons will all line up. Okay, so the bottom line is above TC and below TC, on the far right, it's solved. And then above TC in this area here, we don't know how to explain these phases. Okay, so this is, I love these kind of like, they give you too much food, the food's terrible, but they don't give you enough, okay? Interesting point about the high temperature superconducting dome. As I mentioned, on the right side, it's a simple metal, below the dome, it's a superconductor. Thing about a dome is that it's highest in the center and it's lower on the sides, which means on the right side, okay, if it's weakly correlated, it's a simple metal, TC is driven down. But as the correlations increase across here, TC goes up, and then if you keep increasing the correlation, it goes down again. In fact, we know on this side, these strange kinds of phases actually steal spectral weight from the superconductor. So, but even though these correlations push down the superconductivity, you don't get high TC without it. So there's some kind of delicate balance between the strange kind of correlations that happen up here and high temperature and unconventional superconductivity. And that's why I spent the first few years studying this. Now I'm studying up here. So here's some examples. I told you this is heavy electrons. Above this dome here, the electrons get incredibly heavy. Doesn't work out. I mentioned the electron pneumaticity. These are my data. This is where it's superconducting down here. And this whole area here is where the electrons turn into these liquid crystal-like shapes. And here's something called stripes, where the electrons just line up across the sample. And there's dozens more. Now I'm gonna, I don't know if I have time, can I have 5 more minutes? No, maybe not. Okay, so I guess what I'm gonna do, maybe I won't get to this analogy, but what I'm gonna mention is that there's dozens of families of these superconductors, and they're really complicated. And we've developed dozens through the years of ways to measure, grow, and compute that didn't even exist. Even in the last 5 years, it's been amazing. This is where I think I'll finish with this. This will take 3 minutes, I hope. Okay, so I had an inspiration. Can this work with a good analogy with gravity? So I was, as you know, the Nobel Prize in Physics in 27 was for LIGO, the discovery of gravity waves. And here's an example that Kip Thorne used to use a lot. And that's a picture of the distortion of the space-time continuum. And here's the sun and maybe the Earth. And you can see that the sun distorts much more than the Earth. But there's an interesting distortion. I thought, can I make an analogy with conventional superconductors? Well, it took me 56 hours. But what I'm comparing is this distortion in the space-time continuum that Einstein came up with, and the distortion in the lattice background that Bardeen, Cooper, and Schrieffer came up with for conventional superconductors. Okay, here we go. A couple of slides here. Okay, gravity wave detector. They first detected 2 black holes colliding. As we all know, it's the most amazing engineering that has ever been accomplished, I think, ever. The energy was more than the combined power of all light radiated by all the stars in the universe. But it's not photons, and it's not matter. And what it did was it moved things less than the size of, like a tenth the size of the proton, and that's how they detected the gravity waves. But the bottom line is, before LIGO, we could only measure the universe with matter or light. For the first time, we have a whole new microscope or telescope on the world that measures something completely different, which are gravity waves. What we have in quantum materials is we have many quantum matter detectors that I mentioned. There's a whole slew of new measurement techniques, better crystal growth techniques, and better computation techniques. So Mr. Newton said, the apple fell on my head. It's 1/r². But there were a few problems with it, like immediate accident at distance. Mr. Einstein said, there's a problem with that. And he figured out the general theory of relativity, that the microscopic theory of gravitation was a distortion of space-time continuum. But to me, more than even discovering gravity waves, because we knew we'd find them, there was so much evidence out there, is that will this new telescope on the universe help us understand what we don't understand in the universe, specifically dark energy or dark matter? We don't know if it'll tell us that, but at least it's a new way to look at the universe. Quantum matter. Mr. Fermi, my hero in physics, found ways to understand simple metals. Bardeen, Cooper, and Schrieffer said, it doesn't work for this metal. It doesn't work for this superconductor. And now we have all these methods to measure. Can those help us understand all those phases of weird electron matter? Second last slide. Two great unsolved problems in physics. Gravity, Newtonian classical. Forces between objects derived from mass and positions, right? We know that's 1/r². It's where are the masses, okay? And how big the masses are and their distance. And in simple metals, the properties are derived from the crystal atoms and their positions, as I mentioned earlier. So there's some analogy there. General theory, masses create distortions in the background. BCS superconductivity, electrons create distortions in the background. Very interesting. So the idea is, will LIGO help us understand these great questions of the universe? And will all those nano LIGOs that we have help us understand all those unconventional superconductors that we have in front of us? So basically, that's the bottom line. We have new and innovative tools, and I'd be happy to answer any questions, and I thank you.
Thank you.
Too long, sorry.
So
we started
welcome to open your mic and ask questions or put it in the chat. Yeah, thank you. Actually,
Dr. Greene, thank you for
thank you.
speaking to our community tonight. It was lovely. Do you think the next breakthrough will be from some accidental alloy that someone makes or a measurement?
I love that question. Thank you. So I've been working on predictive design of new superconductors for a long time. I didn't show the slide here, but we've been trying to do this forever. It turns out that we can't predictively design any correlated electron material, whether it's a thermoelectric for heating and cooling, or it's a superconductor. No one knows how to predict those things. All of those little dots on the TC versus time, none of them were, I mean, they will argue I predictively designed this, but none of them will predictively design. The answer to your question is yes. And then I put up pictures of my heroes, right? Some people that have made these breakthroughs and they claim to have predictively designed it, but they've each discovered one family of superconductors. If you could predictively design it and it wasn't serendipity, you would have discovered two families of superconductors. So yes, I believe the next breakthrough in the new materials will be serendipitous.
so it's not that dissimilar from protein folding, where
Yeah.
Well, thank you.
But we're working toward predictive design. But it's been not, you know, one of the reasons is that if you work on predictive design, you fail so much, you lose your funding and you realize it's it's easier to keep your funding by measuring that quantum matter and publishing those materials. So.
Anna.
Yes, I have a question, hopefully a simple one. So you mentioned that in this new quantum matter, there are these states of electrons that are correlated on scales of maybe 8 lattice constants or something like that. So how many electrons are correlated in those?
Oh, that's a very good question. So these materials actually have a very low electron count. Okay, so typically in a normal metal, you have like 10 to the 26 electrons in a, an Avogadro's number of electrons. So these materials can have 10 to the 21, 10 to the 20, and some of them even less. They're very low density. In fact, some of them that are actually lower temperature can have 10 to the 16. Okay, so in the material that I mentioned there, that was one of the iron-based superconducting, one of the families of the iron-based superconductors. So if we say 8 lattice constants, and there's valences 4. So I would say it's probably like 10 electrons. That's a wild guess, okay? Because it's such a low electron count. So that was, by the way, that was imaged. So my work found a way that I can detect where the pneumaticity was, but I can't image it. And there's a couple of groups that use STM to image it. But they can only do that because I told them that it was there. So.
That's remarkable. Cool.
Other questions?
What's the airspeed velocity and everything?
Don, you must have a question.
I have a question. Did it sort of explain, like you need the quantum physics to explain superconductivity, right?
Yes.
Which seems different from regular conductivity, I guess you mentioned.
Well, that's always a tricky question because certainly quantum mechanics is going to play a role in electronic conduction in copper, okay? But it's easy, okay? So I always have to say that you're obviously more educated. If you're more educated, everything's quantum, right? Everything's quantum. But what happens in these materials, you can't really understand how these electron states come in. You take a simple metal and even a non-simple metal, but just a metal. And what happens is that you just look at where like I said, where the lattice, where the ions are and what the ions are made out of. And these DFT calculations tells you the result. And I can go into a lot more detail, but what happens in these materials is that the electron, that's why they're called strongly correlated electron systems. The electron-electron interaction is stronger than the electron lattice interaction. So all of a sudden the lattice doesn't dictate it. I will also tell you that when something goes superconducting, you can't tell it by looking at the lattice. So you get a completely different change in its properties. It goes from a normal metal, you go below, in a conventional superconductor, you go from normal metal, then you go below the critical temperature, and the properties are completely different, okay? And you can't tell by the lattice. Nothing changes in the lattice. So it's the electron-electron interactions, and that's really hard to calculate. They call it many body effects.
Oh, thank you.
Other questions?
I did have one more actually, which was just for an application that you mentioned was the windmills. So then you would need the liquid air inside the center of the turbine.
That's right. That's the only place you'd need it. You'd need it inside where the transformer is. So, we talk about applying superconductivity to the grid. You don't want to really run it across long lines. You're not going to gain that much anyhow. You know, what you lose in long lines or medium lines or short lines is all about the same, because you run the long lines at 300 kilovolts or something. And so because the voltage is so high, the current is very low and you don't have a big resistive loss. That's why it's done that way. But if you can find localized areas where you can apply superconductivity, it's really useful. So get a superconductor in your backyard.
So does that mean they're going to start making liquid air on the towers?
Oh, there's so much liquid air. Have you ever had a wart burned off?
Pardon me?
Have you ever had a wart burned off?
No.
Okay,
Well,
but that's
yeah.
liquid air. I mean, you know, people have done that. So it turns out that liquid helium to cool, you know, conventional superconductors is incredibly expensive. And over the past few years, the price has shot up. There's politics involved in there, but it's really, really, really expensive. And if you want to go even to lower temperatures, you have to use an isotope of helium-3, and that is almost impossible to get now through the Homeland Security, another whole story. So these things can be $30 a liter, $100 a liter, depending on where you buy it, for just the regular plentiful liquid helium, because helium is a critical element. It goes up in the air and you don't get it back, right? Liquid air is like 20 cents a liter. So it's much cheaper and much easier to cool, except we charge more to the doctors. It's easy to transport, it's easy to take, and you can stick your hand in it, but you can't do that with liquid helium. It just will disappear too quickly.
Other questions? Leanne, I see that CERN was called out in her talk.
Yeah, the high luminosity LHC and the MagLab collaboration. I'm going to stress that now.
Yeah, so I can, let me just go on for like, let me wax on or wane, whatever it's called, for another minute. So they had just discovered this material. Niobium-310 was never practical. And serendipitously, by the way, they discovered if they doped it with hafnium, it changed the critical, how much more current it could take. And all of a sudden, it just helped the stuff immensely that it's now the material of choice for the high luminosity upgrade. So I was at a AAAS meeting about 3 years ago where I'm on the board. So I get to interview people on stage and introduce people, and Fabiola Giannotti was there. And of course her talk, she's a rock star. Talk was awesome. The MagLab was all over her talk. And she gave a talk at the Applied Superconductivity meeting this year. It was all virtual. And the MagLab was all over the talk. And when she's asked, how high luminosity can you go? She goes, it's up to you guys. And this was actually a collaboration between the Magnet Lab, Fermi Lab, and LBNL, Lawrence Berkeley Labs. And the actual windings are taking place in California and being shipped to CERN from there.
Very cool.
One final question. Patricia, you look puzzled. You're on mute. Patricia, yeah.
Okay. No, I don't think I am unusually puzzled.
Okay.
I thought we were going to get through a Zoom meeting without you.
No, it was
That doesn't happen in those days.
really
So
interesting.
what's going to happen
how
when this pandemic
stuff
is
I
over?
haven't thought of. I mean, you know, that I don't know about. It's like I almost don't have enough knowledge to develop my questions yet.
So
Okay.
Patricia, have you ever had an MRI?
Oh, now you're on mute, Bran.
Oh, I heard him.
Patricia, have you ever had an MRI?
Sorry, I just, Vicky turned her sound down and then neither one of us could hear. So what was your question?
I said, have you ever had an MRI?
Why, yes, I have, but I dope myself up enough that I don't really remember it.
Well, didn't they go through the quantum mechanics before they put you in there?
I just left that to the experts.
Sign a disclaimer.
So the advantage of high temperature superconductivity is that you need less cooling than you do for conventional superconductor in these MRIs. And so you can get things, you can get the detectors closer to the person and increase resolution that way. So that's one of the things that people are looking at. There's a whole slew of applications. I could go on, as you can tell, for a few days here.
No, I'm thinking of the just the practicality. Closer to the person sounds to me like a narrower tube.
Well, no, I don't mean in a tighter thing. We're talking about that if you can go closer. One of the things that one of my friends who studies these things and has done a lot of MRI applications is that you can get the things closer to, so you can have a half of a, you can take someone in an ER, they come into the ER and you just put them up against this thing and you can get a scan really quickly without having to roll them into a tube.
Oh.
So that's what I meant.
Oh.
Yeah.
Wow.
Now, that would be a real practical application, because right now it's hard to access the technology.
So Patricia, do you get like a card where you can click off your MRIs when you get to 10 MRIs?
Right. If I get to 10, I get a free one.
Yeah, right.
Yeah, that would be nice.
Yeah, I'm hoping I'll have one next year, and then it'll be 2 years before I have to have another one. Although I did wonder, that image we were looking at was the MRI image. Was it a brain or was it a frog? I was having trouble telling.
It was
Frog.
A rat.
a rat.
It was a rat. Oh, I was
Yeah,
wrong.
the more the
I
funnier
said it was a single
With the,
frog.
yeah, I could tell those were the eyes, but.
Okay, any last questions before we sign off? Thanks so much.
Thank you,
Yeah,
guys. Thank you for the questions.
Thank you very much.
Wonderful.
Thank you.
Fun.
Bye-bye.